Good morning, everybody. Thank you for your patience. Sorry, we just had a few small technical difficulties. Today's training is going to be the IBC solar modules. We're going to go through the portfolio. Florian from our head office in Germany will be presenting to us a bit later. I'm just going to quickly do a IBC introduction, just run through our platform and our store. So we'll get that started quick for you. I'm going to do a share. You can all just let me know if you can see my screen. All right. Zane, can you see my screen? Yeah, okay, perfect. All right, guys. Just to let you know, the special that we're running this month is on it's modules, inverters, and storage bundle. So a whole system purchased together, you'll receive a 2% discount up to 15 kilowatt system. And the code for that is 2SPRING. Just to remember, when you place the order on the store, you need to put the coupon code in before you place the order. It can't be done afterwards, so just remember that. All right, so if you're logged into your IBC store, you'll see at the top there you've got Portal. If you click on Portal, it will take you to the landing page, which has all of these tiles. This is essentially where this is your hub to go to where you need to your shop, to your price list, PP manager, whatever it may be. So let's just start off with the price list information. If you click on that tile, it will take you through to this page where you can download an Excel version of the price list. The price list is then in South African rands as well as US dollars. And you just change your discount code and you can search through there. Alternatively, you can use the shop as well. It's very easy to navigate. You've got all your pictures and your data sheets and everything like that. All right, back to your portal hub. You've got the online shop in the top there. If you go to your online shop, you've got the drop downs at the top where you can go and check out the PV modules, your inverter brands, storage, mounting systems, accessories, e-mobility, any items that we have on sale, the promotional goods and services that IBC also sells. And scroll a little bit further down, you've got the brands that we are partnered with. You can scroll through there and select by brand, and it will take you to the shop page for the brands. And then your cockpit, that will just give you an overview there of your search, quick orders, or your current shopping cart. And then if you click on My Documents, that takes you through to this page. There at the top, you've got My Data. So this is your business data, my shipping address, your documents, which I'll cover now, and then any coupons that you've got available, and then saved shopping cart. So if you purchase items on a regular basis from us and you want to save that shopping cart, you can. It's then just a one click to add all the items to the cart, and you can then go to your checkout. At the bottom there, you've got your documents. So any open orders that you still have, any outstanding invoices that need to be paid, your last deliveries, as well as an overview of the invoices that have been sent through to you. All right, so when you click on a item, so we're looking here at the IBC modules, we're looking at the 410 watt bifacial module. You've got an overview there of the specifications of the item. And then on the right-hand side there, you've got the tiered pricing model as well. So between 1 to 35 pieces, the pricing, then 36 to 359. And then you can see your tiered pricing model there. And then gives me your unit price at the bottom. And you can then just adjust the number of units that you want, add it to your shopping cart and carry on. All right, if you click on the download section there, it will take you to the bottom of the page. This will give you all the downloads available for that specific item. So we've got data sheets, warranty, installation manuals, and then any certificates that you might need. And this will be for all the items. And then in the middle of the page, you've got the availability graph. So this tells you the availability of the stock at the moment and the expected forecast for the stock that will be coming in. So if something's not available right now, you can check maybe it's available in the coming weeks. Then once you go to your shopping cart, you've got two buttons there. You've got request a quote, so that will just generate a quote then on our side. And if you want to place the actual order to generate a pro forma invoice, then you're going to click on continue at the bottom of the page. There's your shopping cart just above what's in the cart. And then once you go to continue, it will give you a summary of your order. You've got the total line value and then the VAT amount and then the total inclusive of VAT. And back at your portal overview, if you click on PV Manager, so PV Manager is an IBC in-house design software. The software is very similar to things like Helioscope or PV Syst. It's fully integrated with our store. So if you go to and you do your design on PV Manager, it will generate a bill of materials for you, which is also one click to add to the store. And that will go into your shopping cart and you can then place the order from there. You can also save designs. So if you have a general design that you want or that you use, you can save that design and will obviously save your bill of materials as well for one-click shopping. Then the technical services that IBC offers, we have commissioning services that we offer, on-site callouts, and we can also do remote commissioning and assistance. We can do single line diagrams, and then PV designs as well. Then if you go to order management, this will be similar to my documents. It will take you to your confirmed orders, any open invoices that you currently have, your recent shipments, and then an invoice overview. Then we do have financing options. So we do have a 30-day payment terms as well as 6-month repayment, which is powered by Lula Pay. All right, and then just a reminder on the coupon for this month, that is 2 spring, and that is for a inverter, modules, and battery system up to 15 kilowatts. All right, Florian, are you ready to start presenting on your side?
Yes, I'm ready.
Fantastic.
Okay, I try to share. One moment. Okay. Hi to everyone. I present you today the modules of IBC Solar. Some words about me. I'm Florian Mechler. I'm the product manager for the modules at IBC Solar, and I'm around about 2 years in the company. Yes. When you have questions, I think the best is you write it in the chat, and when Sané or someone from IBC Solar see the questions, please come to me and ask them. Yes. That's for the beginning. Now we come to the agenda, what I want to talk about today. First of all, I want to give you a general overview of a PV module. So what is a PV module, which components are in it, and so on. So it's very general and an overview over PV modules. Then we come to the current market trends. Some of the trends you know already, but perhaps there are also some news about the trends. Then, of course, the technologies. So with the technologies, I mean the cell technologies like TOPCon, PERC, and so on, and to bring them in the right order and see, what are currently the main technologies and so on. Afterwards, I want to present you our bifacial module and the benefits of it. And when I'm ready with all the benefits, I will show you tests about bifacial modules to see what are the benefits of an to use it as a bifacial module, and afterwards I want to give you a good feeling by buying IBC modules, and because I want to show you what we do more than competitors or some suppliers. Yeah, that will be the agenda. So we start with the general topic. Okay. For this, I want to, you see, we start more or less with sand. So Silicia is like sand. So you use sand for the modules. And now we can go over the different steps to come at the end to a finished module. So we have the Silicia. Then in the process, you come to a low purity silicon. Afterwards, you come to a high purity silicon. I think you cannot see my mouse, so moment. Okay, so we are at a high purity silicon. And in the past we had the polycrystalline type, and nowadays we have the monocrystalline modules. So I start with the monocrystalline and say afterwards some words what is different for the polycrystalline. So for the monocrystalline way or process, you took some rod with a monocrystal on the one end, and put it into a big bottle with a liquid silicon, and then you take it out very slowly, and because it's so slowly, it gets dry, and it builds a very long monocrystal, and that's why you talk always about monocrystalline modules, because it's one crystal which is very long, and this very long crystal is called ingot. And to come from an ingot into a wafer, you have to slice it. So you make pieces out of it, and then you cut it into a wafer. Afterwards, you do some surface processes. For example, do some fingers on it, so the very, very small metal on the surface, and a little bit bigger things, like here you can see perhaps these are the bus bars. So you put these things on the surface, and the cells, and afterwards you have a cell, and this cell you take into the module, and the module of course comes into a system. And what is now different to the polycrystalline, it's only the beginning with this, which is different. So you have the liquid silicon you put into a crucible. Then you have a big block, but this big block is a polycrystalline block, because it starts on many ends to get dried, and that's why you have the polycrystalline structure. And then you slide the block into small blocks, and then you can slicing them into the wafer. So this is only the difference between poly and monocrystalline. Then coming to the next slide to see what are the main components of a module. We start from the back side. I think it's better. You see the junction box or boxes nowadays. You haven't anymore one junction box. Most of the time you have 3 junction boxes with the bypass diodes in it. Then you have the back sheet. To glue the back sheet better to the solar cells and to the glass, you need an encapsulant. In the most of the time it's EVA. Then you have the solar cells. Then on the front side, of course, again an encapsulant. Then you have the tempered glass, and then the aluminum frame. And the aluminum frame holds the complete plate with the different components. So the glass cells and so on is put into the frame, and most of the time it's with a silicone glued in. That's to the module in general. Then coming now to the current market trends. Perhaps you heard something about full cell, half cell, and perhaps already about triple cells, and why do we, or why we have this different cell types or cutting types. In the past, there was only full cells, and no one asked why it's a full cell. And then they found out when you cut the cell into two pieces, then you have some benefits, because you see it on the on this graph. When you take the this is the current, and when you cut the cell into two pieces, then you have in each piece half of the current. So it's only the half. And why it's important to have the half current? Because the energy losses are the current in squared multiplied with the resistance. So when we halve the current, then it's significant better for the energy losses. So we lose not so much energy anymore. And that's why the complete industry goes to half cells. And another benefit is for half cells, you see it on the picture below. When you have a full cell module, the bypass diodes are at the end, and you have three strings in a module. So it's like here, this is one string, then you have here a string, and the last string is here. And when the first row is shaded, then you lose 33% of the power. So, and what is different with the half cell? You have not anymore the bypass diodes at the end, they are in the middle. And then you have not only three strings anymore, you have six. So here's one, here's one, here's one, and the three other on the bottom line. Okay, so you have the same shading as before, but because you have the bypass diodes in the middle, you have only around about 16% power loss, because it's only a string with 16% roundabout, which you lose. Yeah, that's the reason why you have a better shading management. So perhaps you know already some modules with triple cut, and perhaps you have the question why IBC has no triple cut module. We also looked at it, and at the moment we are sure we find only, or most of the topics are not beneficial for a module. So when you cut a cell into three parts, then of course of the one cut more, you have more stress for the cell. So the cell edges are almost a little bit critical, and when you cut it one more time, then of course it's more critical, because of the one process step more, you have also more error prone, and one more step costs, of course, a little bit more. So you have also higher production costs. And it's, we are not sure if you have really shading advantages, because where do you want to put the bypass diodes on to have a better shading situation? You're already in the middle, and what will you do with the bypass diodes to get it better? So from our point of view, a triple cell will not have a better shading management, and it's more difficult to connect triple cut cells than a half cut cell. Yeah. Then going on to the wafer trends. I tried to put an updated graph on it. So we are currently in 2023, and you see the main market is M10. So at the moment it will stay M10, and when you look into the future, it will still stay on M10 wafers. Also, there will be a growing part of G12 wafers. So in the future, I think it's more or less half for G12 and half for M10. And perhaps in a few years, we will see coming bigger wafers than G12, but we will see. Yeah. Perhaps one step back. What are the sizes of the wafers and why they have different names like M and G as a letter. You see, in the past, we comes from M2, then G1, then M6. M6 was around about until last year a main wafer size. And nowadays, I said it before, it's M10 and goes up to G12. So when you look really good on the picture of the wafers, you see the difference, the differentiation between G and M. The M has cutted edges, and the G is a normal square. Why is the differentiation? And why is here cutted? It's not cutted. I told you at the beginning of the webinar, you cut the wafers out of an ingot, and an ingot is round. And to have less waste, you try to make the square really big, and that's why the edges are missing. And here you have bigger ingots and have a complete square, so you have more waste. And the reason why you go to bigger wafers is, of course, saving costs. You see the area increases very much, and that's the reason why the trend is going to bigger wafers. And there is still another trend, which is not in the graph at the moment. We see a change from squared wafers to rectangular wafers. So we have already some modules which are not squared, so the length is different to the width. Yeah, but you will see it in the next slide a little bit better. So some words about the module sizes. What means the different wafer sizes for the module size? You see this, I tried to get the right sizes to each other to have a better comparison. So a module with M6 wafer was around about 1.82 square meter big. And when you go with the step to M10, you see it goes wider, so the width goes bigger, but the length goes smaller. And you have then a module with 1.95 square meter. So you have a bigger module at all. And now with the wafer trend with rectangular wafers, we call it M10 plus. You stay with the same width than the M10 module, but the length increases with 4 centimeters. And the reason is to come near to the 2 square meter. So now you are at 1.99 square meter. And the reason why the 2 square meter is so important is Germany. In Germany, there is a regulation with 2 square meters. So you can only put modules less 2 square meters on the roof. and all others you cannot use for a roof application. And that's the reason they try to go near to the 2 square meters. Then also some pictures, what means for 72 cells or for bigger modules when you change the wafer sizes. With an M6 wafer, you're a little bit over 2 square meters, so it's 2.17 square meter. When you go to an M10, it's just really long and a little bit wider, and you are already at 2.56 square meter. And with a G12 wafer, you are really near to a 3 square meter module, so it's 2.83. And what we also see for module sizes or for the frame sizes, it goes to 30 millimeters in residential application and 35 millimeters to power plants. But it could be a little bit different in the South African market. There I'm not so deep in. Yeah. So what are the effects of the frame height on the system? When the frame height goes down, the module is not so stable anymore, and yeah, so it makes sense to test it better to see the environmental influences on the module. And we decided to look on the system. So we are not only looking as a supplier. A supplier looks only on the mounting structure or only on the module side. And as we are a wholesaler and we have our own system, we in our point of view, it makes sense to test the complete system, because there are some topics which we see which are different to only testing modules or only testing mounting structure. So when we test in a system, for example, the clamping area could be less, because the clamps are smaller than the clamps are in from the test of a module maker. On the other side, when a mounting manufacturer tests, they take a plate, a very stable plate, for testing the mounting structure, and both are not really realistic, which is in the field. So we are sure it's better to test in a system. Yeah. Now coming to the technologies, but perhaps is there any questions until now? Sunny, are there any questions in the chat?
Hi, Florian, not yet. I will, yeah, when you ask again, I will check again. All good.
Oh, okay, great. Then coming to the technologies. You can say the PV technology is divided into 2 big topics. It's the wafer-based, the wafer-based PVs and the thin film cells. The thin film cell isn't, very important or not so on focus at the moment, because we only at the moment which make sense are not good for the environment. That's why we focused on wafer-based, and you know already the modules which are wafer-based. So it's crystalline silicon, and yeah, we have the monocrystalline silicon at the moment. But it's still good to know that there is thin film cells, because the industry is working on emerging thin films. So they try to put all critical critical things out of the cells to have a good cell for the environment. And this is important because in some years there could be tandem cells, and for having a tandem cell, you combine thin film cells with wafer-based cells to get higher efficiencies. You can see it also here on the right side. This is a research about the different cell technologies. You see in 2023, it's the main market are perc. We see a trend to TopCon, so the gray fields are TopCon. In my feeling, TopCon is at the moment already bigger than you see it here, but it's only a feeling of myself. Yeah, and you see here the dark blue on the top at 2030. This is tandem based. And there is also another trend. It's the back contacted cells. So you see no bus bars at the front anymore. And of course, to not forget heterojunction, it's also a cell technology. So here we have an overview about the different cell technologies or the main cell technologies, and you see it in a over the time how it developed. So in the past you have BSF, it's like polysilicon modules or cells. Then it comes to perc, and now we see the changes at the moment. I think you see it also, the changes to TopCon. Also heterojunction plays in this same time, and a little part is IBC cell technology. The IBC means not IBC Solar. The technology is not from IBC Solar. It's a different technology. It has only the same name. It's a back-contacted technology. And afterwards, you see it like here, the tandem cells. So to come to better cell efficiencies, you need a tandem cell. Also here on the right side, it's again research. You see beginning from 2025, there could be the first tandem modules in the market with quite good cell efficiencies. And here you see also, or you could see why there is a change from perc to TopCon. When you see here, here's it quite near the dark square to the orange square. So it's very close to each other. And over the time, it goes wider. Yeah, and the reason is the perc has a limit of 24.5%, and that's the reason why most of the producer goes to TopCon. Yeah, here you see also the trend from P-type modules to N-type modules. Here's 2023, and you see the part of N-type goes bigger. Okay, now in a different view, how was the path of the efficiency? You see in the past it was poly, so it was around about to 2016, and then we go to a monocrystalline module, and the technology was perc, and it was around about 23%. Yeah, and we are like here at this line. In the past we had P-type, so all on the left side it's P-type. Here on the right side it's N-type, and you see there are different possibilities to go on. So it could be TopCon and it could be heterojunction. So when you look near to the N-type cells or cell technologies, the first generation there is like PERT, so it's near to PERC, but on N-type cell technology, and the evolution goes to TopCon. So TopCon is really near to PERC or PERT then, and there are two main main cell technologies. It's heterojunction and IBC. Heterojunction works with an amorphous surface, and IBC it's interdigitated back contacted cell, so it has no boost bars. Okay, what could be the future development when you combine heterojunction cells with IBC cells, or the technologies when you combine them, you get an HBC cell. So it's like a backside contacted heterojunction cell. And when you combine the heterojunction back contacted cell with TopCon, then you get a TBC cell. So that's combines all the benefits into one cell, but it's a future development, and we will see it in the future. Okay, that's all about the theory part. Now we come more or less to the practical part. So what means this for a module? And I want to bring an example. It's our IBC monosol ES10 HCNBF. I included also the data sheet that you know about which module I'm talking about, also after the webinar. When you look into the presentation, that you know it's this module. Okay, perhaps for beginning, why most of the suppliers goes from perc to TopCon? The reason is when you are looking on the structure of perc, and then to the structure of TopCon, you see, okay, the coating is more or less the same. Then the emitter, it's the same. Okay, not completely the same, but here is it an N positive emitter. Here is it a P positive emitter. Then you have a substrate in the middle of the cell. Here is it a P silicon substrate. Here is a negative silicon substrate. Then you have a rear passivation, more or less here. And then you have again coating on the backside. So we have only two layers which are additional. So you have the tunneling layer on it and the passivation on the front. And you see the cells are really near to a perc cell. And that's the reason why most of the suppliers or manufacturers go to TopCon. They can use the production line of perc by adding two machines. It's very placative, but you add some machines, more or less two processes, and then you come to a TopCon cell and to a TopCon module. When you want to go to a heterojunction module, you need everything new. And that's why they decided to go to TopCon. It's cheaper for the manufacturers. Yeah, then we come to the advantages of the module I showed you 2 slides before. So the module is more efficient. They has more efficient cell because it's a TopCon cell. And here I try to show you why TopCon has more is more efficient. You see the line of perc and the line of TopCon. And you see the TopCon line is always over the perc line, but the growth is not so good in the past. So when you see until 2020, it's not so the growth is not so high. It's for perc which goes much higher. It increases much more. And the reason is because they do more researches on perc until 2020. And then they said, okay, they are more or less near the maximum limit of 24.5. They put more researchers on TopCon, and that's why it increases here very fast, because they had a change in the research researching. And the reason is, I said it before, perc cells have a limit of 24.5%, and TopCon cells has a limit around about 28 to 29 roundabout. So that's why you go to TopCon, and the cells are more efficient. And so in whole, or as a conclusion, you have more energy production with a TopCon cell. And you will see on the next slides why it is like this. So advantage 2 is you have a better temperature coefficient. So this means when you look on the bottom line, these are the different temperature coefficients over the technologies. You see, beginning from perc as a full cell, it was like 0.37. Then it comes to monoperc half cells. It's 0.35. And TopCon is now at 0.3. It's not a big step. It's only 0.05, which is the difference. But when you look what is the differences in percentages, it's 16.5% as a differentiation. And that means we have an efficiency increase of 16.5%. What does this mean for a module? I said both the perc module and the TopCon module starts with 410 watts. And then we see what happens when the cell temperature increases. The line goes down and the cells goes up. The cell temperature goes up. Normally, I would say for South Africa, it's between 75 and 85 degrees. So you have here more production of 2.5% at 75, up to 3% at 85 degrees cell temperature. In absolute, when you look what means this in absolute numbers, it's like 8 watts for one module here in for this points, and here it's like 10 watts from a TopCon module to a perc module. Okay, it's perhaps not that much, which is the differences between them, but you have not only one module on the roof. Perhaps these are 20 modules or what else on the roof, and with 20 modules, you have already 200 watts as a difference between a TopCon module and a perc module. And 200 watts, I think it's really much. Then coming to the degradation. When you look on the performance guarantees, you see the perc module or the perc guarantee goes up to 25 years, and TopCon guarantees you 30 years of performance. But we have also a second topic. That's why we have two advantages. Also, the degradation per year is less. So we start for TopCon with 1% first year degradation, and with perc, it's like 2% for the first year. And then every year degradation of a TopCon module is normally 0.4%, and for a perc module, it's around about 0.55%. And what means that in the energy production, you get round about 3% more energy out of one module. And that means you have a bigger energy production with a TopCon module by only changing the technology from perc to TopCon. The next advantage is the low light behavior. I know this graph is a little bit placative because it's not complete right, but it's also not wrong. You can say a TopCon module starts 1 hour earlier a day producing energy and ends up 1 hour later than a perc module. Why is it like this? The N-type cells have a lower resistance, and because of the lower resistance, the carrier can better goes to the boost bars and then goes into the and we can have it as energy. And also the carrier have a longer life. So this is very important when it's low light. So you can produce more energy in low light situations. It's very difficult to tell you how much percentage is more. That's why I tried to put it a little bit placative. It's 1 hour earlier, which the module starts, and 1 hour later, the module ends up. Yeah. Then the next advantage is the ES10 HCNBF module has 16 boost bars. Why it has 16 boost bars? You can say per additional boost bar, you have 4% less internal resistance and have 0.18% more power output. Why you have it? Because when you have more boost bars on a module, you have more lines to get the energy out of the cell. So it's easier for the carrier to go to a boost bar. You can imagine like train stations. When you have more train stations, the way to one train station is shorter. Yeah, but of course, when there should be also some negative points, because everyone would put the complete surface with boost bars on it. So you can also say with every additional boost bar, you have a shading area. And the shading area increases by 0.18%. And that means a power loss of 0.11%. And when you put it into a graph, you see it like here on the right side. You go to a boundary, and with 16 boost bars, with a diameter of 0.28 millimeters, it's more or less the optimum number of boost bars for it. So you get the best situation to get all the power out of the cells. Yeah, but you have also another benefit of the multi-boost bar situation. It's the reduces of the micro cracks or the effects of a micro crack, because when you take it into a picture, you have only one boost bar on a cell, and you have a micro crack on the left side. Then half of the cell cannot produce any more energy. When you have 2 boost bars on a cell and you have a micro crack on the left side, then it's only 33% power losses. And that's the reason why more boost bars are better for the effects of micro cracks. So when you have a micro crack on a cell with more boost bars, it affects not so much than with less boost bars. Okay, coming to the advantage of the glass-glass surfaces. Of course, with a glass-glass surface, we have a higher protection against environmental influences. That means you have better stability properties under snow and with wind. But you have also better protection against some animal damages, perhaps when there are some birds going under the modules, or some, I don't know, cats or something else. you cannot have any scratches into the back sheet. So it's safer with a glass backside. Then you have also longer warranty periods. And I looked also in the warranty sheet. I see that you also have the 25 years product warranty for the ES10 HC and PF. So you have a very long guaranteed module. So and so you have a revenue protection and you have higher returns because you know, okay, the module will definitely live for 25 years with the product guarantee. Okay, what means it for the cells or for micro cracks? With a glass surface, you avoid micro cracks better. You see it here in this in this picture. This is a glass foil module. When you have some loads on the surface, then you have some pressure into the glass, and it pulls on the backside, but it also pulls on the cells. So you can have micro cracks in it because the neutral zone is like here. When you have a glass module with the same glass thicknesses on the front side and on the back side, it's now this picture here. You have the you have some stresses on the front side, you have some stresses on the back side, but the cell is in a neutral zone in the middle. So you avoid micro cracks in the cell because there are no stresses in this zone. So it's better for the cells to have a glass surface. Then, of course, you cannot have any degradation of the backside of the back sheet, because when the back sheet isn't there anymore and you have glass on the backside, it cannot degrade. So also no water can come into the module or what else. Then with glass on the backside, you have one component less which can burn. Glass normally do not burn, so you have higher protection in case of fire. But I'm not sure how it is in South Africa. In Germany, you can normally go near to the firewalls. So please attention. Always observe the present building regulations to be sure that you can go near firewalls or what else. And the last thing, it's more or less a conclusion. Of course, all topics based on additional income. So when you are safer, you have longer guarantees that a module live longer. You earns more money from the module. And the last topic, it's the bifaciality. Bifaciality means that not only the front side produces energy, also the backside produces energy. But there is an issue with backside because the backside cannot produce the same energy as the front side. Or that means it depends on the technology of the cells, how much the backside can produce in comparison to the front side. For perc, it's like 70% of the front side, which the backside can produce. For TopCon, it's 80%, and for heterojunction, it's 90%. So with the ES10 module, the backside can produce 80% of the front side. What means this for producing energy? With 420 watt module, when you have 6% bifaciality, so 6% comes from the backside. The 420 watt modules can produce 441 watts. And you see it can go, we see it can go up to 25%, but it's more or less a theoretical value. You can go up to 525 watts with a 420 watt module. So you get more for the money. Now we comes to the tests of some bifacial modules to show you what means this in realistic scenarios. Perhaps for the beginning, for a bifacial module, it depends on the albedo effects. So the backside gets the light which goes on the ground and comes back to the backside. So the best situation is like snow, so a white ground. It's the best reflective situation for the light. And as darker the ground goes, like here or here or here, the worse of albedo. So the you have a worse albedo, and then the reflection of the sunlight is worse. So if you want to earn the more money from the backside, you should have a very bright bottom. So we tested it also on a test plant. You see here we have some grass imitation and some stone imitation, but on this side we have a monofacial and a bifacial module, and also on this side we have a monofacial and a bifacial module. And you can say as a conclusion, you can get round about 9% more yield, additional yield with a bifacial module by an installation as a power plant without any tracker or something else. So I think that's really much when you get 9% more with a bifacial module. And this 9% was tested with a perc module. I said before, it depends on different cell technologies. The perc module can only bring with the backside 70%. When you have a TopCon module, it's more than 9% from the backside because of the better bifaciality factor. Okay, then what we also tested it as a vertical alignment. You see, so the blue line is a test with the south direction, and this green line is an east-west system, like this here. And you see, you have the benefit of it is that you have 2 points, highest points. You have it in the morning as a higher point, and it goes down during the day, and it goes up in the evening. What is good about this? It's good because when you're working during the day, you have a higher peak in the morning where you take a coffee or a shower or what else, I don't know. And in the evening, when you do have any meal you prepare. So for this case, it is really interesting also, but I do not know if it's in South Africa the same. When you when you do not use the energy for yourself, and you get the money for putting the energy into the network, then you get money for it. And most of the time during the peaks during midday, you get less money than in the morning and in the evening. In this case, it makes also sense to have an east-west system. Here you see also the numbers behind vertical alignment. When you have a bifacial module in the direction of the south, or in the south direction, you get the most kilowatt hours out of a module. When you have a monofacial in the south direction, it's the second best situation, and as an east-west, it's the worst. But of course, you could get more money because you can use the energy better in the morning and in the evening. So it depends on when do you use your energy most. And the last thing we tested with bifacial modules is what is the different additional yield when you use silver foil on the ground in Aerofix or black foil on the ground. And this is also very interesting to see the different albedo effects. With a silver foil, you get round about 3.5% more additional yield in comparison to the black one. And at sunny days, it means up to 4.2% additional yield. So also for flat roof applications, it makes really sense to go with a bifacial module. Okay, and now we come to a bigger part. I have to look on the clock. Sané, how many time do we have left?
Florian, you can, I think we have about 10 minutes left, but you can finish up. It should be fine.
Okay, I think I give some impression about what we do with our testing procedure with new products, but also with testing the complete modules. So I go over this. So how do we secure our quality promises? We are working with the SunLab. It's an independent testing laboratory, and we do the several tests. The first test we do, or one of the tests is determining the highest performance. So you can say it's a flasher test. We put the module like here into a dark room, and we give a photo or a flashlight, and then we see how much energy the module produces. And the flashlight brings 1000 watts, so it's a standard situation. And then we see can bring the module really the watts which stands on the type plate. The next test we can do is, the EL measurements of PV modules. For this, you give some current on the module, and then with a special camera, you look on the module, and then you see by shading situations if the module have microcracks or not. I try to show you a picture later. Then we have some static mechanical load tests. You see it on this picture. So we have some arms which give pressure on the module, but it can also pull the module to see how the module works with snow and wind. And for this, we give also some approvals and say, okay, for aeropics, it's a maximum of, for example, 1,200 pascals. But when we give you these numbers, we are sure there will be no problems with the module. Then we have also a temperature cycling test. It goes up to 80 degrees. And we try how it works in warm conditions, but it can also go down to minus 40 degrees to see how it works with very cold conditions. Then we do also moist heat test to see if some moist can go into the module, and if the module is produced very good, or it will be there some issues by coming moist into the modules. Then we can also have a detection of voltage induced degradation. And we do some measurements of insulation resistance under wet conditions to see is the module safe. So you cannot get any energy through the backsheet or something like this. I would say we go over this. So normally we do not only do one test. So for the static load test, for example, we have to do also a EL measurement and a performance measurement to compare the emission to compare the performance from before to the test after the static load test. So what we do more than others? We test under real conditions. This is not required by IEC standards. So normally I described it to the beginning of my presentation. For IEC, the module makers test the module with, they called it super clamps. They put them really, they took very high torque on this clamp that the module cannot come out of the clamp. And we test it under real conditions. So with our, for example, with our Aerofix mounting structure, with the right torque we use in the field, and so on. Then the next thing is the EL measurements. We do also EL measurements. For IEC, it's not required. So we know if there is a micro crack after the static load test. After IEC, you do not know it. And what we also do is we do the same test 3 times, not with the same module, of course with the same type, but not with the same module. So we want to exclude a one-hit wonder. So with 3 tests, we know, okay, all modules of this type can stay with this load. For IEC, it's only 1 test, which is required. So our quality standards are really unique. I'm really sure that there is not something else in the market which is that hard than ours. Yeah, perhaps what is also very interesting for us, it's not acceptable any inactive cells, any micro cracks or something else, and we say up to 3% power loss is the maximum, which should be after the static load test. The reason is why we said a maximum of 3% is still okay, because of the instruments. It cannot measure better than 3%. But to see what IEC said is IEC permitted up to 5%. So we are quite near half of the regulation of IEC. So our test conditions are much harder than IEC said. Here are the EL pictures. So every bright cell is a good cell, and every dark cell is a bad cell. And you see there is sometimes a cell between, so it's still bright, but you see the cell, the micro cracks in the cell. So at the moment, the module brings the when there is a micro crack into the module, it brings still the same power than before. But during the time, the micro cracks has influences, of course, to the energy production, and that's why we said, okay, micro cracks are not okay for a module. Yeah. Then we have also optical deviations. Perhaps to make it short, when you see any optical things at a module, it's not acceptable. Like some damages on the frame, when the frame is damaged, or when there is too much space between the clamp and the frame. So what can we guarantee? No loss of the system performance due to permanent wind and snow load, because we tested, and no premature aging due to environmental influences, of course, why we tested, and no material fatigue. Yeah. So now I'm finished with my presentation. Are there any questions now in the chat, or you can also ask them now?
Florian, it looks like you have done a really good presentation and answered all the questions. It doesn't seem like there's any questions at this moment. Thank you very much for the presentation. I think it was very insightful and informative. There's one comment saying thank you for a very interesting presentation by David. So yeah, thank you so much for this.
You're welcome.
Okay. So thank you, Florian. Enjoy your day. Thank you for